Our first video in Chapter 6 for Chemistry 121 at UND is on balancing chemical equations. When balancing a chemical equation, what's being done is making sure that that chemical equation does not disobey the law of conservation of mass, which says that matter cannot be created or destroyed during a process. Now, for a chemical equation to follow the law of conservation of mass, they must be balanced. When a chemical equation is balanced, it means it has the same number and type of each atom on both the reactants and the product side of the reaction. The first step to writing a balanced chemical equation is to write the correct symbols for each molecule or ionic compound in the equation. For instance, to write the reaction between hydrogen and nitrogen to yield ammonia, we have to remember that both hydrogen and nitrogen exist as diatomic gases, meaning they have a subscript 2 behind them. Now, here we have the correct chemical formula for each reactant and product. The reactants are on the left side of the reaction, the products are on the right side of the reaction, and they're separated by this yields arrow, which points toward the products. Now, the second step in balancing a chemical equation is to add coefficients where they're needed. Coefficients go in front of the molecular or ionic symbols. We can never change the subscripts. The subscripts are the numbers that go behind the atoms. Now, changing the subscripts changes the identity of the molecule or ionic compound, and that is why we cannot change them when balancing a chemical equation. The first thing I like to do when I balance a chemical equation is to tally up my initial number of each atom on both the reactants and the product side. On the reactant side, we have hydrogen and nitrogen, and we should have those same two elements on the product side as well. Initially, we're starting with 2 atoms of hydrogen because of the subscript 2, and 2 atoms of nitrogen. On our product side, we have 3 atoms of hydrogen because of this coefficient, or excuse me, the subscript 3 behind hydrogen. And we have no subscript behind nitrogen. That implies just 1 atom of nitrogen on the product side. Now, here's where we can add coefficients to bring up the numbers of elements where we need it. Let's look for an easy ratio. Starting here, we have a 2-to-1 ratio of nitrogen. To bring it up to the same ratio, we need to increase the number of nitrogen atoms on the product side. So we need 2 nitrogen atoms on the product side. Since we only have 1 already, we can add the coefficient 2 in front of ammonia to give us 2 atoms of nitrogen. This also changes our number of hydrogen atoms. We need to multiply the coefficient by the subscript to tell us how many hydrogen atoms we have. So 2 times 3 is 6. Now we have the same number of nitrogen atoms. Hydrogen is different. To get us to 6 hydrogen atoms on the reactant side, we need to add a coefficient of 3 on the reactant side of hydrogen. That way 3 times 2 gives us 6. So what we're doing here is finding where we have more of that type of atom. For instance, when we balanced for hydrogen, we had 6 on the product side and 2 on the reactant side. We want to work by increasing the number of the atom on the side that has fewer, not by decreasing the number on the side that has more. So we add coefficients to increase the number of each atom until they match up. Now, a balanced chemical equation must also have the lowest possible coefficients. So for instance, if we were balancing and we got this reaction, 6H2 plus 2N2 gives 4NH3, this would not be the correct way to represent this equation because we can divide each of these coefficients by 2. And so by dividing by 2, we would get the reaction as balanced as we did previously. So it's important to just double check all of the coefficients to make sure there's not some factor by which they can be divided to get to smaller whole number values. You want to make sure your coefficients are whole number values and not fractions. Now let's practice balancing some chemical equations. In this example, we have the reaction of iron 3 chloride and magnesium oxide to give iron 3 oxide and magnesium chloride. I'm going to begin by tallying up each number of atom. We have iron, chlorine, magnesium, and oxygen on both sides of the reaction. And I'm going to write them in the same order on both sides here so it's easier to compare. On the reactant side, we have 1 iron atom, 3 chlorine atoms, 1 magnesium, and 1 oxygen. On the product side, we have 2 iron from the subscript 2, 2 chlorine from the subscript 2, 1 magnesium, and 3 oxygen. Now let's look where we can increase the number of some atoms. We have 1 iron on our reactant side and 2 on our product side. We can fix that by adding a 2 coefficient in front of iron 3 chloride. That gives us now 2 iron atoms and 6 chlorine atoms. So iron matches up. Now we have 6 chlorine atoms on the reactant side and 2 on the product side. We can increase our number of chlorine atoms by adding a coefficient 3 in front of magnesium chloride. That gives us 3 magnesium atoms and 3 times 2, or 6 chlorine atoms. Now everything is balanced but magnesium and oxygen. We have 3 of each on the product side and 1 of each on the reactant side. Magnesium and oxygen are in the same compound on the reactant side in a 1-to-1 ratio. And so if we add a coefficient 3 in front of them, that increases both magnesium and oxygen to having 3 atoms, and we have all of our elements balanced. Just double checking, we have the lowest possible whole number coefficients, and if you notice, we didn't need to add a coefficient to iron 3 oxide, which is fine. The coefficient of 1 does not have to be shown, it's just not written down. The next example here is the reaction of calcium chloride and sodium phosphate to give calcium phosphate and sodium chloride. Now I chose this example because we see we have the phosphate polyatomic ion on both sides of the reaction. When this is the case, we don't have to balance for both phosphorus and oxygen. We can balance for the phosphate polyatomic ion as a whole. So when I write the chart to tally up each element, I can write calcium, chlorine, sodium, and then the polyatomic ion phosphate, PO4, with a -3 charge. And I can do the same on the product side. And we can do this because notice we don't have phosphorus or oxygen anywhere else in the equation. All right, now initially on our reactant side we have 1 calcium atom, we have 2 chlorine, 3 sodium, and 1 phosphate polyatomic ion. On the product side, we have 3 calcium, 2 phosphate. The subscript 2 out here behind the parentheses means that we have 2 units of phosphate. And we have 1 sodium and 1 chloride. Now let's see where we can increase our number of atoms or polyatomic ions. We could start by increasing calcium. We have 1 calcium on the reactant side and 3 on the product side. If we put a coefficient 3 in front of calcium chloride, that increases calcium to 3 and chlorine to 6. Now, the next thing we can do is increase our chlorine atoms. We have 6 chlorine on the reactant side and 1 on the product side. We can add the coefficient 6 in front of sodium chloride to increase both chlorine and sodium to 6. Now, sodium and phosphate are still not balanced, so what we can do is increase our number of sodium atoms from 3 to 6 on the reactant side by adding the coefficient 2 in front of sodium phosphate. That gives us 3 units of sodium, or 3 times 2, excuse me, 6 units of sodium. And now our phosphate increases to 2 units of the phosphate polyatomic anion. And looking here, we have 3, 6, 6, and 2. So we have the same number of each type of atom or polyatomic ion. And so now this equation is balanced. Again, checking for anything we can divide. We do not have numbers that can be divisible by any other number, so we have the lowest possible coefficients in front of each compound. Next, we have this reaction, which is a combustion reaction. Here, I'll start again by making that table. We have carbon, hydrogen, and oxygen on both sides of the reaction. We have 5 carbon, 12 hydrogen, and 2 oxygen on the reactant side. We have 1 carbon, 2 hydrogen, and 3 oxygen on the product side. Now, when balancing here, it's a tiny bit different than a previous reaction because on our product side, we have oxygen in 2 different places. When any element is in more than 1 molecule or ionic compound in a reaction, you want to save balancing for that element until last. So we should balance for carbon and hydrogen before balancing for oxygen. Let's balance for carbon first. We need 5 carbon on the product side, so we can put the coefficient 5 in front of carbon. That now gives us 5 carbon on the product side, and 5 times 2, 10, plus 1, 11 oxygen on the product side. To balance for hydrogen, we need 12 atoms of hydrogen on the product side. We already have 2, so we have to add the coefficient 6, because 6 times 2 equals our 12 atoms of hydrogen. That also changes oxygen. We now have 6 times 1 plus 5 times 2, so 6 plus 10, which is 16 oxygen atoms. Now here, for our O2, we can put the coefficient 8. Since we're done balancing for carbon and hydrogen, now balancing for oxygen, we had 2 and 16. Adding the coefficient 8 in front of O2 gives us 8 times 2, or 16 atoms of oxygen on both reactants and product side. Now, all of our coefficients have the lowest possible whole number values. Now, if you're ever looking to check to see if you can divide by any factor to decrease your values of your coefficients, you need to be able to divide that same factor by every coefficient. So even though we can divide our 8 by 2 to get 4, we cannot divide the coefficient 1 here in front of pentane to give us a smaller whole number value. And so it is not appropriate to do any reducing of our coefficients in this case.